Okay. So one of the things that I always feel we have to refer back to is that in our industry, we have lots of different entities that have been set up to help guide us how to do things correctly. And in all our different projects that we do, if there's a spec book, you're going to find all kinds of references to ASHRAE. You're going to find all kinds of references to NEBB or TEB or ABC or ANSI. You're also going to find references to AMCA, where AMCA is a little bit different. Rather than just having a publication, they do testing as well. And we do testing at AMCA for our products. And these are entities that have been around for a long time. They spend a lot of money on research, and they come up with different standards on how to do things. Most of what I usually talk about is out of the ASHRAE fundamentals. The last time fundamentals was published was in 2017. If you go to chapter 37, you'll find all the information about airflow measurement in there. There's also a long publication called Standard 111, which they test various manufacturers, different technologies, and they come up with how system effects affect different types of products, different technologies. In our HVAC world, equal areas is really the method for setting up sensors that's accepted most widely. And we're going to talk about another one in a minute. But you know, whether it's NEBB, TEB, AABC, or AMCA, they all talk about equal areas. And the idea behind equal areas is that whenever we do this type of work, we always want to find how to accurately measure what we're doing as best we can. And this is a simple method of coming up with a grid of sensors, and the larger your area, the more sensing points you're going to be measuring. Usually it starts off at about 16 points, but it will get up to about 64 on what they plan. So equal areas, like I said, is the industry standard in general for doing airflow measurement, whether it's a circular, rectangular, or square area that we're measuring. So equal areas is our standard. The other things that we see in a lot of these publications is where to locate a probe or an array correctly. And the reason this is so important is that, like so many other products that we use in the HVAC industry, airflow devices have to deal with system effects. So if you have an elbow and you have it with or without turning vanes, there's a difference in how to locate where you're going to locate your probes or your array of doing things. And these are all set up by the various entities, and they show you how to do it correctly. And we just follow along, because this is basically just the physics of the air moving through the ductwork. And like when we do ductwork design, we don't analyze. I mean, in general, we don't analyze, this elbow could be moved a little bit this way or that way. There's a lot of other constraints, physical constraints, on how we do the ductwork. So we basically work with the ductwork, and then where is to be airflow measurement, then we'll look at those areas in detail and deal with it as best as possible. There's another method of airflow measurement. It's very similar to the equal areas. It's called log to Pepachef. This is really the ASHRAE standard. And the problem with log to Pepachef versus equal areas is that we need a fully developed flow within the duct. So we usually need about 30 duct diameters to do this correctly. And the sensor density is a little bit different. It's not a linear way. It measures the middle more than the outsides. We do these on the nuclear power plants. The reason we can do it on a power plant is because, in general, the mechanical equipment that we're supplying air to and the areas where we have to measure the air are quite a distance apart. So we're able to get those 30 duct diameters to do it correctly. And you know, like I said, when we do things like nuclear power plants, that's not an issue. We do log to Pepachef. And like I was saying before, the reason that we want to make sure that we locate our sensors correctly is because there's a lot of dynamics going on within a duct. Today, just about everything is VAV. We see very few applications today that are constant volume. So what's going on within the duct is always changing based upon what the air volume is that's moving through there. So there can be these eddy currents or backflows going on within a duct. And if you don't observe the rules that these entities have done testing on to find out which way, or excuse me, where to locate your devices correctly, you're going to have issues with inaccuracies within the duct, even if you have the correct sensor density that they prescribe. And going along with that, every job we have, there's always a balancer who's involved. You know, he's going to take that information that I just been talking about, and he's going to take a probe. He's going to drill a couple holes in a duct or wherever, so that he can do those equal areas with his probe. He writes them all down on a tablet, and writes them all down, and then he'll take the average of all of them, and he'll say, that's the CFM that we've got, or that's the feet per minute, and I've got this area. So we've got this this airflow measurement that we can say accurately represents what's going on within the duct or an outside airflow measurement. There is a little bit of a problem from what I've seen, in that because there are these dynamics going on within ductwork or an outside air, when the balancer does his job, when he does his job, it's very rare where he'll go and take airflow measurements at 100% and 75% and 50% and 25% and something low like 5%. So when he takes an airflow measurement, he's taking it at full flow. And we don't really know how the dynamics of the airflow within the duct really change, because he's only taking it at one reading. So this is something that's kind of a gray area after the fact. And as we know, in the world of VAV, the systems very rarely operate at full flow. I mean, you usually see them flow at 60 or 70% most of the time, and how they're reacting or moving within a duct or an opening could be very different than what it is at full flow. Okay, that's for talking about the basics of airflow measurement and the different technologies. Let's move on to outside airflow measurement. It's become a very big and popular topic, especially the last couple of years because of COVID. Before we only did airflow measurement because it was a lead project said you had to have it. In California, we have Title 24. ASHRAE talked about 62.1. They also talked about 189.1. I should have put that down. Sorry, I forgot to put that down. But those were really the only reasons that we did outside airflow measurement. Other than hospitals or schools, outside airflow measurement weren't really all that popular in general. But because of COVID, everybody's looking at how to increase indoor air quality. And like we used to say for so many of the lab projects, so dilution is the solution. So if we're bringing in more outside air, theoretically we're bringing down the number of contaminants within the air within the building. So that's our big concern these days. Let's take a look at outside air. There's a lot of different concerns about outside air, especially when we're talking about rooftops. And there's so many different types of rooftops out there. In a lot of cases, it could be with a hood. And if it's a hood, is there a single hood or are there multiple hoods? In a lot of cases, there could be a louver. Is there a vertical louver or a horizontal louver? So how we're going to do airflow measurement is affected by the physical properties of the device that we're actually working with. I just talked about that. Sorry. The other thing is that when we're looking at outside airflow measurement, there's always a damper involved. So whether the damper is a horizontal damper or vertical damper, is it a opposed blade or is it a parallel blade? These are all things that affect the accuracy of an airflow system. And if you don't design around the actual, the way the unit's built, you're just, taking a guess at where you're going to put things. Something that we've also found that while we like to see a opposed blade damper used on outside airflow measurement in general, the way the air flows through the dampers is also an issue. When you have a opposed blade damper, there's going to be areas that I call hot spots, and there's going to be areas where there's nodes, where you have an open area at all times. Those basically represent an area where you're going to have high velocity at all times. But where you have your shaft as an axis of rotation for the damper, those are going to act as nodes, and you're going to have low velocities at those areas most of the time, unless when the damper is fully open. So we need to, in general, locate our probes in a fashion that's at right angles to those dampers so that we get a good average over the device. So there's a lot of little nuances that go into outside airflow measurement that that when we look at ductwork, don't even begin to touch on the dynamics that are associated with choosing or how to set up your outside airflow measurement system. At Paragon, we do a lot of different things that we can do to make a damper airflow system measurement work together correctly. So, in a lot of cases, we'll do, on the top left-hand corner, this is like a min OA and a mod OA, and they just happen to have the airflow measurement on the min OA, so they can prove it that they're bringing in outside air. The smaller ones on the bottom left-hand corner, just show some small outside airflow measurement systems. These were fully set up with the damper, with the transducer and the temperature sensor all set up together. There's some other ones where we have some bigger dampers, and it's all set up in this would go in an outside air duct that was going into an inside unit or air handler within the unit. So we're always looking at all these different things. We're talking about, turbulence. We want to make sure that we're getting the right number of sensing points within the system. These are all things that come into play. I've got some real world examples of what we can do with the airflow systems that we do. Start off with, like I said, in years past, outside airflow measurement wasn't all that popular. And here's a system where there's an existing unit. We found out the dimensions of the hood, and we fabricated an outside airflow system where they could take the hood off, mount the outside airflow system onto the outside of the unit, bolt the hood back on, and then you're good to go. All the stations that we build as a minimum are 16 gauge galvanized, which is quite a robust piece of metal. Will last a long time, even if it's outside. If you want to paint it, you can paint it, but we do all kinds of things like that. For retrofits, here's another retrofit where the hood was in place already. It happened to have space where we could drop in a bell mouth on this one. You can see they're in the process of putting it together. There's some DP tubing that's hanging down, and underneath there you've got the door open. So this one just dropped in where the hood was. This one worked out a little bit easier. Here's one that was built, I'm thinking like 10 or 15 years ago. This happens to be at Sandia Labs. A couple of big air handlers within the building. Just to the left of it is a shaft where they're bringing in outside air into the building, feeding into these outside air flow stations. You can see that the averaging PITOT tubes again are at right angles to the damper, so we can get a good average across there. Always at right angles and always before the damper. That's like the basics. Here's another retrofit where we've taken a larger damper and they've sectioned off an area so they can do minimum outside air. This one basically stays open all the time, and the rest of the dampers around it can modulate. Just some ideas of what we can do. Another item that we do, I'll show you a couple of different variations on this. In the real world, when you're measuring outside air, we want to keep the velocities up a little bit more. I mean, even though we can measure down to 100 feet per minute, there's real world effects that are happening outside that can influence our airflow measurement. So what we found is that we want to try and keep a minimum amount of airflow at 180 feet per minute. By doing that, we find that we can measure better accuracy even at the low airflows. So in a lot of cases, we'll have like a rooftop unit, for example, and the frame size can be from 15 to 50 tons, just as a number. Well, that 15-ton unit is going to have the same size opening as the 50-ton unit. If we can decrease the area a little bit, we'll get the velocities up some, make the outside air damper work better, because instead of just cracking open and letting all the air in, it'll control a little bit better. So we do stuff like this with the sheet metal for our airflow stations all the time for outside airflow measurement. Here's a similar one, similar idea. This was on an indoor unit though, and we actually blanked off a large section of the outside air damper so that we get the velocities correct and measure airflow nicely. So something that was factory fabricated, came out as a system, and they just put it together. Here's another system where this was for a large air handler. And we, fabricate this. It was a two-piece outside airflow measurement system. And as you can see on the bottom, there's a bit of a blank often on the sides, drops right in, matched up with the bulkheads for the dampers. So it was, an easy system for, this one happened to have been done in the factory. So it's a nice system for putting it in, and there's like no guesswork associated. You just drop it in. We provide a drawing that goes with it. There are issues with other ways of doing airflow measurement, and I was just out at a hospital over here in Sacramento, where they had a airflow straightener and diffuser plate that they were using for outside airflow, and this was something that they actually maintain on a regular basis. But you can see that this kind of stuff gets clogged up with particulates that are in the air on a regular basis. So, there's a lot of things that you need to look out for when you're doing outside airflow measurement. Like when you're doing outside air, we really don't look at pressure drops associated with it. And usually for rooftops, that's like never calculated in. What pressure drop do you use for a system like this? Do you use the initial, because the airflow straightener will have some pressure drop associated? But once it starts building up particulates on the inlet, what number do you use then? And then try to balance a system where you thought the air pressure drop or assume no air pressure drop for outside air versus your return air pressure drop, and try to make that work. So there's a lot of complications associated with outside airflow measurement. So what we like to say is we like to make the outside airflow systems such that they drop right in. They're made to work with your system, whether it's the full size or we cut down the size. We build these things every day, all day long. And just to go over a couple of items that breaks it down for you. This using an airflow station like we provide for so many projects, it's a lower cost overall. It's factory built. Factory labor is cheaper than field labor. They just drop right into place. So you don't have to look at something later on and say, what was that guy thinking when he put this in? Because he did some kind of screwy thing. There's like no guesswork associated with this. If you can read an arrow, there's a little arrow on the airflow station always. And if you can connect up a couple of tubes to a transducer, you pretty much have a perfect installation every time. So this really takes all of the guesswork out of doing airflow measurement. So many of the times, we'll send these to the manufacturer, and they'll put it in at the factory. So you also have single source responsibility for this type of application. And it really works well and provides an accurate method from outside airflow measurement. Moving on to, outside airflow measurement, I had mentioned earlier that we do our testing actually at AMCA. The left picture shows an actual test going on at AMCA. We're testing a couple of transducers at the same time. AMCA runs all the testing, so we have no say in the matter. They'll ask us, do we have it set up right? We'll say yes, and they'll run the test. AMCA certification is on so many of the products that we use: fans, diffusers, louvers, all kinds of. They do like 17 or 18 different products, and here's the proof that we can provide accurate airflow for an outside airflow system or an indoor one, and we're within 0.35% accuracy. And this is by AMCA, not by somebody, not by us. It's third party, and you're not going to find anything that's really more accurate than 0.35% accurate. And like I always tell everybody, You know, accuracy is great at AMCA, shows us that the system is, you know, spot on, but getting the details right is where it's all at. And that's something that Paragon does differently than all the other airflow measuring manufacturers. We try to get the details right on every single job so that we can give you the accuracy that you're purchasing to start with. This, you know, this is like a graph that shows some, you know, the difference in accuracy between something that's 0.5 and let's say 5 or 10 or 15% accuracy. You know, the industry standards say that we can be 15, you know, excuse me, 10% accurate, and that's supposedly okay. But in an outside air application like Albuquerque, where we take, you know, the Albuquerque weather and utilities, and we look at a 4,000 CFM unit because that's what AHRI says the average size. I mean, if you're off by 10%, in 10 years, you know, 4,000 CFM is about a 5-ton unit, roughly. I mean, you can buy another unit for the amount of money that you've wasted on utilities because you've assumed that, you know, whatever you measure for the outside air is okay pretty much. So, you know, it pays for, the systems basically pay for themselves within the first year if you get something that's accurate. Because IAQ is such a big topic today, I want to put this slide in there. Paragon has this device called the multi-trans. And the multi-trans has a lot of different applications that you can use it for. So we've been talking about outside air, but the other thing that goes along with indoor air quality to a great extent is our filter banks. And we can measure the filter banks. We can measure as many filter banks as you have in the unit individually. So this ensures that, you know, if you have your filters loading up, it can send a signal to the building management system saying, okay, it's time to change the filters. So you're changing the filters before they're fully loaded. And you're also changing them based on the usage of the actual unit. You're not using it based on some company or whatever the schedule is that they had for changing the filters. You know, so that can save a lot of money in terms of not having to change filters when they're really not ready to be changed. So there's a lot of applications that way for filter loading. Dedicated outside air units have become a lot more popular these days, making sure that you have a balanced airflow or you have a balance on your heat exchanger. These are things that we can do very easily with the multi-trans. It's a nice product that can be used on new or retrofits. And again, these things are always calibrated at Paragon for your exact application. So basically it's plug and play and it's ready to go whenever you want to utilize a product like this. You know, finishing off on outside airflow measurement, there are a number of what I call checkbox outside airflow measurement methods, and you know, they might save you a couple of bucks on your first cost, but the single point devices really do not capture all the dynamics that are going on with an outside airflow measurement system. So yes, you can say you have an outside airflow measurement system if you have one of these devices, but you're not going to get the dynamics. And you're also going to find that in general, when you use a system like this, you're going to have some kind of accuracy issues moving down the road because it's going to be getting particulates building up on it one way or another, and you're going to have you know, issues with the actual device moving forward. So that's what I had on outside airflow measurement. Is there anything I can answer for anybody with regard to that? Otherwise, I'm going to move on to our next most popular method application for airflow measurement, which is fan arrays. Any questions I can answer? Okay, moving on. Fans and fan arrays. We all know that fan arrays are extremely popular. I remember when University of Phoenix stadium was built with the fan arrays there. That was, you know, a huge game changer in general for the air handling units in general. I mean, I had been using smaller fan arrays for a lot of years, but you know, the University of Phoenix job was like, you know, really out there, and you know, really brought a lot of fan arrays to a lot of people, people's attention. You know, the owners wants to see and control the fans and monitor them. And I also said that fans are probably the most common point of mechanical failure. And the reason I say that is because just statistically, if you fans are we have the most of, I mean, compressors have a certain statistic associated with failure, but if you have a lot of fans, there's a chance that there's one of them going to fail somewhere along the way. So we want to know what's going on with them. So fan arrays are very popular, and we're going to talk about fans and fan arrays at this point. Basically, in the world of fan measurement, on the top left-hand corner, for many years, fan inlet probes that Paragon and others build have been basically the industry standard for measuring fans, and they work fine. You know, if you have a smaller fan, there can be issues, basically choking off the inlet cone of the fan, but in general they work pretty well. But it's kind of like an old standard. I mean, it's something that works well, but you know, we have something else today, which is the piezo taps or piezo rings, which Pace brought to the world a number of years ago, and it's a really elegant, much more elegant way of doing it, because we really don't have anything in the inlet bell anymore. It basically works with Bernoulli's principle, and we can have, you know, we have a differential pressure, and we have a venturi, and it's a very nice system. It's very elegant for doing airflow measurement at a fan, and I think it's, you know, just terrific. There are other technologies again available. Vortex shedders are offered to do at the inlets of the fans, as well as thermal devices. But you know, looking at this from, you know, seeing the developments over the years, like, do you really want to have anything in the inlet bell if you can avoid it? So, you know, I don't necessarily know if you know, putting probes there unless you absolutely have to is the way to go. They're only measuring 1 or 2 points versus an area, so you might not get the dynamics of what's going on. You know, in fan arrays, there's also the issue of, you know, every fan does not push the same amount of air. So, you know, measuring a small area or a fan or whatever, you might not capture what's going on. Basically, what these manufacturers have done is they've taken their other airflow measurement products, and they've kind of like rebranded it for outside for fan measurement. So it's very limited in that it can only measure a couple of fans. So if you have anything more than like 8 fans, you're done, you know, with one of their devices. You have to go to multiple devices. The product that we have, and we'll talk about a little bit more, it's called the FATS 1000. I'll show you some more slides on it. Basically, we're taking and this is for a larger fan project. We're taking that venturi, we're taking the taps, we're mounting a transducer right near the fans, having short tube runs. You know, it's a clean and simple method for doing it. You know, we have like a very modular method of doing it. This is what the FATS 1000 looks like. It's basically a control panel or an HMI human machine interface, touchscreen display, and then we put these transducer modules at the fans. So when we do something like that, okay, we come up with an architecture that looks like this. And what we're able to do is we can put the FATS 1000, the display and the touchscreen wherever we want. And those heavy black lines on the diagram show the Cat5 cables. So we can put the transducer modules at any of the fans or, fan arrays. And we can also link into that the outside airflow measurement. So again, this is another savings associated with it that you don't see with other manufacturers, is that, we can do this one HMI, which is a touchscreen display. You only need to have one power connection. You only need to have one building management connection. All that information is transferred by doing it that way. So it's a unified and simple way of doing something for a large fan array system with or without outside air. The graphical user interface that we provide with the device is set up so that it looks like your fan array. So whether you have, 40 fans, or if you have 5 fans and it's, 5 fans horizontal, one, 5, we'll set those displays up to look just like your fan array. So if there is something that needs to be looked at, it's a really good diagnostic tool. We can also link in the outside air, with the system, and it gives you really a comprehensive way of looking at all your airflows with one device. And it's, quite a nice way of doing something. We do so many projects with the Nortec units, just for an example. So that's kind of what I had to say about outside air, fans and fan arrays. And I want to do like a summary at the end here and pull all the stuff that we pulled together. So we've discussed, a number of items along the way. And, I look at this as kind of like the long view or some conclusions to draw. We have a number of different entities that have been around for many years. So there's lots of experience, and there's experts that are making recommendations. And, selling any of those recommendations short is going to compromise your accuracy and the longevity of the product. We also need to consider what we do, and if we specify or we install a product, how it's going to hold up over time, and whether the the owner will be saddled with a lemon or whatever you want to call it, or do we want to give them something that we feel confident is going to keep working for a lot of years to come. Again, first cost is always a consideration, but the cost of maintenance, it needs to be considered. Costs associated with accurate measurement, and also getting an exacting installation. These are all important items for the owner that have to live with it. And documented systems. So again, we want to know what we're getting before we get it. So really, we have been depending upon AMCA for so many of our products. So an AMCA approved product is usually a good way to go. I touched on this. The specs are all written around. We all have these boilerplates from the different entities. Let's use them. Longevity of a product. So many of the products that we, everything we put in there, we want, or we know it's going to be there for years to come. So even if you can, even if it's an equal cost, why not get the best product? I was thinking, earlier, why would you pay more for a Volkswagen than an Audi? I mean, an Audi is basically a Volkswagen that's been, a little bit more refined and things like that. So, what we're providing basically is an industrial product at a commercial price. And if you to look at some of the competitors, Air Monitor and GreenHeck, they offer thermal devices. If you look at their websites, you're not going to find thermal devices on any of their industrial or power plant, any of their power plant offerings. They're only going to offer the averaging PITOT tube like we manufacture. And why? Because it's more reliable. Thermal just isn't reliable enough for industrial applications. So why not give the owner the advantage of a more reliable product to come? Part of the reason that it's more reliable is it has so many more sensing points. We're using either equal areas or log to Pepperchef, which the thermal cannot offer. The other thing is that because we have all these sensing points, there's an inherent redundancy that you don't see with either thermal or the vortex shedders. If you have a thermal device or a vortex shedder, and they have fewer sensing points in general than we do, but let's say just in general, if you have 4 sensing devices and one of their sensors for whatever reason gets fouled, whatever the reason, you're only going to read 75% of the value of what you're actually doing. And I was just doing a project for a big hydroelectric plant, and they needed to stay within 3% accuracy no matter what across the range. So if they were to do a thermal system and they had one or a couple of sensors fail, it would throw their system right off right away. And the vortex shedders have the same issue. If you lose one sensor, you're going to be off by a large percentage, and it's going to be a large percentage decrease in the amount of air that you're measuring. So then, if you're measuring less outside air, we can, I'll show you in a slide or two what the effects can be of something like that. So we also, I think, offer a number of savings associated with the product. And if you look at the products, like, it's not like a national secret what, my product costs versus a thermal product versus a vortex shedder. We all find out different information, and they're all about the same, within a couple $100. It's not a big deal one way or the other. And in some cases I'm cheaper, in some cases they're cheaper, whatever. But if you can get a product that's set up so that when you go to put it in, or once it's in there, it's ready to go because it's already been calibrated and designed to fit into that particular location. It's not just a kit that they give to you, and you've got to figure out how to mount it, and then the air balancer has to come in and take his readings and set up the device. Wouldn't that be good to have something like that comes right from the factory that's already done? We calibrate our equipment at 11 points before it ships out. So we're getting the whole range of how the device works to make sure it works correctly. It's not just, set up so that, it's testing one individual sensor and saying, we've got this certain accuracy. We're testing the whole system. We calibrate it for the altitude. When we're doing outside airflow measurement, like we've been talking about most of the time, we provide a sensor so that we can change for the density of air as well as that. So we're not dependent upon other people for doing that kind of stuff for us. So, there's a number of savings associated with the transducer. Also, what we can do is, since we're just using a simple DP tubing, I know that most of the other manufacturers, if you have a electronic device one way or the other, whether it's thermal or vortex shedders, they charge you, unless you buy, the standard are these short cables Well, if you want to put your transducer a couple more feet away, you've got to buy a whole bunch more cables, and they're expensive. I just saw how much they were recently. So I mean, there's savings associated with just where we mount the transducer. So these are all things that are to be considered. Not only is from longevity, but the cost of installation setup. I don't know how many of you read the ASHRAE journal. The April edition had an interesting article from my point of view, or airflow measurement point of view. It's an article actually about outside airflow measurement and how they had to add filtration in a project. This one happened to be in Florida, but they added air filtration for the outside airflow because they couldn't keep the devices online. And they happen to be thermal devices. And I just took one sentence out of there. If anybody wants to look at it, just take out your ASHRAE journal from April. You'll see it's one of the lead articles that's in the journal. It says that they're basically saying that even though they added air filtration before the thermal sensors, there's no reason to believe that this situation will not repeat itself for years to come. We see that all the time. We're involved with, and people get, they come to a point where they want to talk about doing our products versus other products for outside the airflow measurement. Just to highlight a couple of them, and there's others, and heating, piping, and air conditioning. There was an article about Rochester Institute of Technology. This would happen to be on a return fans that we were doing. It was the supply and the return fans. And this was an interesting one because what happened was the thermal sensors were loading up with lint, and they kept on believing that the return air was reducing, so they kept on bumping up the return air CFM because the device wasn't working correctly. Well, at a certain point, they were they brought the return air to 100%, even though it didn't need to be, and they were blowing return air out the outside air dampers. The outside air dampers were seeing 70 degrees during the winter and saying 70 degrees. We need to bring on the compressors. Well, the compressors were short cycling, and so they blew the compressors because the short cycling caused the oil to get hung up in the system, and so the compressors went. So at a certain point they said, we're done with this. We came in, and it's been running for years at Rochester Institute of Technology. Sprint headquarters had an issue with outside airflow measurement. We redid their whole campus, 17 buildings. Right now I'm involved with a lot of jobs in Sacramento for Sutter Institute. Mayo Clinic is doing it across the country. So, people have been doing outside airflow measurement and had made the misstep of doing thermal are changing over to what we're doing. I'm sharing with you our experience. I think a lot of this stuff all comes down to just 4 basic things. And this is something that I talk about most presentations, and it really summarizes things. We have an accurate product. It's AMCA tested. It's not us, saying what it was. It's terrifically flexible. We sell probes, but the stations don't cost any more than the probes. And if you can get a station put in, you're going to have pretty much a perfect installation every time. The product has great longevity. We rarely, if ever, have a transducer that needs to be replaced. And it's got a robustness because the system has so many sensing points. So it's like an inherent redundancy that's associated with it. Again, we've got, a great return on investment. It's probably a lower first overall cost. And because of the savings associated with the accuracy, especially for outside airflow measurement or lack of maintenance that you need to do with it. You know, there's huge savings utilizing our product. This is, you know, something I usually finish up with. You know, this happens to be an industrial application. This is a stainless steel probe, but it's basically has the same sensor densities that we do with everything else. But it's absolutely furry with shredded carbon fiber. And we tested this versus a clean one. And because we had enough ports that we can measure through, it still was within 3% accuracy of what a clean system would be. So, you know, there's this robustness and the durability that we provide. And I think this goes a long way to providing something for an owner that, you know, you don't have to think twice about. That's basically what I have. I'm also see I'm at, we've taken up an hour. I talk too much. Is there any questions I can answer for anybody? Okay, well, I'm glad I covered everything that everybody wants to know.
Yeah, but there's no questions in the chat.
Okay, and so I have one parting thing to say. Use Veritech, use Paragon, and we're happy to help to get the details right and provide you guys with, guys and girls, with an accurate system that you can, you know, not have to be concerned about in the future. Thank you for your time.
Awesome. Thank you so much, Mike.
You're welcome. Have a good day, everybody. Stay cool.